Hey guys, what's going on? So I'm making this video for the classes that I'm not going to be able to see tomorrow, but also additionally for some of the students who are struggling with some of today's concepts. You really want to watch this, and all the questions that we didn't get to, I would go over these before our next lesson. That's really going to help you prepare for when we do go over them again in class. It shouldn't be as unfamiliar the second time around. Anyways, with that said, we're going to go through the whole PowerPoint, each question. If you need to skip to certain parts, go ahead and feel free to do so. I'm going to be giving full explanations, showing full work, trying to give you a how-to guide on how to do this if you are lost or unsure. So let's go ahead and get started. Okay, so we're working on graphing functions, a more difficult version of it, so this is as complex as it gets, and we're going to cover inverses. These are our announcements for the day. So homework 2.3 will be due next class. You'll see that sent out. Our Alex growth, we are still keeping track of that. That'll be due this Friday. Quiz 2.1 will be due in one class. Well, sorry, not due, but we'll take that in one class. Okay, so these are our transformation rules. If you need to go ahead and pause the video and copy these down, go ahead and do so. But you want to have these rules known in some way, shape, or form. What you see over on the left-hand side right here is the mathematical way of talking about these. And in one way or another, you know these things already. So say, for example, right over here, right? When we're adding something outside of the function, that's going to result in a upward shift. Or when we're subtracting something outside, that's going to result in a downward shift. Remember, outside is up and down. So you're probably familiar with these rules in some way already. You just want to know how the function notation looks, because we're going to get questions that deal with function notation, and we're going to want to be able to read that and translate those skills we already have to a problem. Okay, so make sure you copy that down, make sure you know it, make sure you know what each one does. All right, so let's go ahead and get going. So we're finding a whole bunch of things here. Where I recommend you start is always with your vertex. Your vertex is like the center point of your graph. It's the origin for it. You can find everything else from there. So go ahead, start by finding your vertex. We're going to look at this. And remember, we look inside the function and outside. The inside is going to tell us that we are shifting left 1. And the outside is telling us that we are going to shift up 2. Okay, so that makes a vertex of negative, that's going to make a vertex of negative 1 and positive 2. Okay, just like that. So we'll go ahead and graph this on our graph right there. And now we can start finding points around this to the left and the right of our vertex to get an idea of what this equation is going to look like. So let's start by doing negative 2. I plug in negative 2 to this, and you'll notice that when you plug in negative 2 right there, that's going to create a negative under the radical. Negative 2 plus 1 is negative 1, and the square root of negative 1, we cannot calculate that. That makes a imaginary number. So we can't find that. We're going to put NA for this, and that immediately tells us that when we try to go to the left of that, it's just not going to work out. Alright, let's go ahead and plug in 0, and coincidentally notice, right, x was set equal to 0, which means it is a y-intercept. If you need to make note of that, go ahead and do so. Y-intercept is when x equals 0, and likewise, an x-intercept is when y equals 0. So this is good, right? We're kind of killing two birds with one stone. We're finding out the intercept, and we are also seeing what this graph looks like. So we're going to plug in 0. We see that when we plug in 0, that's going to make the square root of 1. Square root of 1 is just 1. With a negative on it is a negative 1. Plus 2 brings us to positive 1. Okay? If you need to write those down, go for it. No shame in doing so. That's how you get to be able to do it in your head, is by writing it down first. Okay, so that dot goes there. We can go ahead and start connecting our dots, and you're going to see a trajectory, right? And this allows you to start getting a feel for it. You can notice, well, we do already have our y-intercept, and we're going to expect some kind of x-intercept over here. So we'll keep on going with the problem, and just keep that in mind, a little bit of intuition that you're building right there. Remember, x-intercept y is equal to 0, so I set that equal to 0, and I have negative, square root of x plus 1 plus 2. Okay, so at this point, now I know you see a square root in there. Do not worry, you're still doing the opposite to get rid of every operation. The same way we're going to get rid of this positive 2, right? We're going to subtract 2 from both sides because it's the opposite of positive 2. We're going to apply that same concept to the square root once we get to it. Okay? But notice we do have a negative in front of both of these. We have a negative in front of our square root. So we're going to go ahead and get rid of that by dividing by -1 on both sides, which gives us a 2 equals the square root of x plus 1. Okay, now comes the time for undoing or getting rid of that square root, and you need to ask yourself, what is the opposite of a square root? And if you want to pause this and meditate on that and come up with an answer, go ahead and do so because it's very foundational that you know this. So, what is the opposite of a square root? Well, it is just a square. So we're going to do a square on both sides, and we're going to see that turns the equation into 4 equals, those will cancel, x plus 1. A little bit more algebra, and we see that x is going to be equal to 3. Just like that, and we find our x-intercept, which tells us it's 3, 0, and when we plot that point, notice our trajectory wasn't too far off. It's kind of what we expect, which is a good thing. Cool, so we have all that information. We can go ahead and start filling in some of it. So the vertex is -1, 2. The x-intercept is 3, 0. The y-intercept is going to be 0, 1, and the domain and range we can go ahead and start talking about now. So the domain, remember, right, as we see down here, the domain is going to be how far left and right we go. So we look at this, what's the farthest left we can go? Well, that's just to a -1. And then put a comma to now talk about the rightmost boundary. What's the farthest right we can go? Well, that's to infinity. Okay, so we got some beautiful coordinates by our domain. We now need to put some end caps on them, which means we're going to choose either a bracket or a parenthesis to put on this to state whether it's going to approach that value or equal that value. We see -1, it can actually equal that, so we put a bracket, and infinity, we can't actually equal it, so we just approach it. So it's a bracket and a parenthesis. Same deal with the range, except now we're looking at the vertical, so we're seeing how far down it can go. Well, it can go infinitely down, so we can put a -infinity. And notice I just put the parenthesis right there. It's because you can never touch infinity, you can only approach it. And then I'm going to go ahead and see how far up it can go. It can go up to 2, and it can't equal that because notice when you look at this, right, how far up does it go? Well, it'll go to 2, and it can't equal it. Alright, so we got all that done, right? And that is most of what we need for this problem. Now, this next part's going to feel a little bit redundant, but it's about understanding how this could be generally expressed or written without specific details. So we're going to talk about the transformations that's going on here, and we're first going to start by identifying the parent function. Now, what is the parent function? It is basically the thing that makes this equation look the way it does. Notice the curve in that, right? The thing responsible for that is the square root. It's going to give it that characteristic shape. That 1 is just moving it left. That 2 is moving it up. That negative, as we'll find out, is going to flip it downwards. So the parent function is just what gives it the shape. So our parent function is just going to be g of x, I didn't choose f of x because that's already chosen up there, equals the square root of x. Okay, that's my parent function, and now I'm going to rewrite the equation above using that parent function and using that g of x notation. Now, this is going to feel, this throws a lot of kids for a loop. It's going to feel unnecessary. It's going to feel pointless. You might not even see why we do this, but here's a simple guide to get you through it. When we look at this, right, we see an x and we see an x, and notice what's around it. There's a square root and there's a g parentheses. So we're going to use a little bit of logic. We see the x is right there, and we see the square root and the g parentheses, so we're going to say the square root is the same as the g parentheses. Okay, those are the same, so therefore when we rewrite this thing up here, we're just going to replace that square root with a g parenthesis. And that's really it. So take a look at how this looks. We are going to do, notice there's a negative in front of the square root, so I first put my negative. Now remember what we said before, g parentheses is now the square root. So we're going to write g parenthesis, and then underneath that square root was an x plus 1. So we put g parenthesis x plus 1. And then outside of the square root was a plus 2. So outside of g parenthesis, we're going to write 2. And just like that, you wrote your general function notation. Okay. Now, why is that important? Because it agrees with the rules that we have back here, right? When we look at all these rules, it has similar notation as to what we're seeing down here, right? And the idea is that when this shifts, right, we can look at this and we can tell it's shifting 1 to the left because of what's inside. It's shifting 2 up, and there's some kind of flipping going on. Now, I know you might be thinking, well, we could have already told that by looking up here, and this is redundant, we don't really need this, and you're not totally wrong, but the idea is that you need to see how this connects to the general form of it. Meaning, if I gave you just this part down here, and nothing else on this page, you would want to tell me that this thing is going to move left 1, up 2, and reflect vertically. Okay? Alright, so now we're going to rinse and repeat. So let's go ahead and go on. So same dealio, right? We are finding the vertex. I read this and I can tell, well, this one is going right 4. And this one is going down 5. Okay, so that's going to give me a vertex of 4, comma, negative 5. I'll go ahead and graph that over 1, 2, 3, 4. And down 1, 2, 3, 4, 5, right about there. Okay, now we want to find some points to the left and the right. We could choose 3 and 5. Those would be to the left and right of it. We plug in 3. And doing some mental math, we see that's going to equal negative 3. We plug in 5, and again, doing some mental math, we're going to see that that is equal to negative 3 again. Which is good, because that means that we are seeing some symmetry in this. This indeed is the vertex. And we can even start to sketch a line and anticipate where we're going to have some action on this graph. Right? Where is it going to intercept? Where's it going to cross? What's it going to look like? Okay, so that's good. We got that done. Let's go ahead and write our vertex down here. 4, comma, negative 5. Alright, now let's go ahead and we can, it's your pick, x-intercept, y-intercept, it's up to you. I'll start by finding the y-intercept. So remember, y-intercept, I'm going to set x equal to 0. So I'm going to plug in 0. 0 minus negative 4 times positive 2 after we take the absolute value, minus 5. Well, that's going to bring us to a positive 3. Okay, again, doing some mental math, you need to write that down. It's how you get good at mental math. And notice, right, this actually isn't too far off from our prediction. That's pretty good, right? 0, comma 3, that works out for that. Now let's go ahead and find our intercepts. So remember, now for the x-intercept, y is equal to 0. So we plug in y equals 0. And and we go ahead and we start finding our y-intercepts. So we're going to set up this equation. And, sorry, I just realized I said y-intercept, I meant x-intercepts. 0 equals 2, absolute value of x minus 4, closed absolute value minus 5. Okay? Doing a little bit of algebra, 5 equals 2, x minus 4, absolute value. We can go ahead and divide both sides by 2. So we would get 5 over 2 equals x minus 4. And at this point, we now have to deal with the absolute value. So we're going to break this apart into two equations. Remember, this is how we deal with absolute values. We have a 5 over 2, which equals the negative version of our absolute value, and a 5 over 2, which equals the positive version of our absolute value. Okay. Now you're going to want to go ahead and solve these. We're running out of space down here, so I'm just going to spoil it for you and tell you that x is going to equal, for this one, a positive 13 over 2. And I'm also going to tell you that for this one down here, once we start to solve that, this one is going to be equal to a positive 3 over 2. Okay. Alright, so we have our x-intercepts. Again, if you're not sure how I got that, just take some time to figure out the steps in between there. That's, your basic algebra skills. We can go ahead and write our y-intercept on here, which is going to be 0, 3. And our x-intercept, which is going to be 3 over 2, 0, and 13 over 2, 0. Okay. Now 13 over 2 may not be a number that you immediately kind of recognize, but when you think about it, 13 over 2 is just going to be 6.5. And we count on this, we see that's 1, 2, 3, 4, 5, 6, and a half, which, again, that prediction is not too far off. And we look at 3 over 2, that's going to be 1.5, which lines up about right there. So it's a pretty good looking graph, right? We're almost done with this. We're going to write the domain and the range. Remember, domain is left to right. And I don't see this thing stopping as far as how far left and right it goes. So it's going to go from negative infinity to infinity. And then the range, well, how far down can it go? It can go down to negative 5. We see that it can actually equal negative 5, so we put a bracket on it. And how far up can it go? Well, it can go up to infinity. Bada boom, bada bing. One last thing, let's go ahead and talk about the transformations. We're going to do the same thing here where we find the parent function. We look at this in the parent function, right? It's those absolute value bars. Those absolute value bars give it the characteristic V shape. So we're going to say the parent function is g parenthesis x, which equals absolute value of x. Okay? Now remember, right? Using that logic, the absolute value is the g parentheses now, right? The x's are there, therefore absolute value must be g parentheses. So we're going to have to rewrite this, replacing absolute value with g parentheses. So how's that going to look? Well, it's going to look like this. So we're going to have 2, because that's outside the absolute value, g parenthesis, x minus 4, and then minus 5. It's getting a little bit cramped down there, but that's what it's going to look like. Notice everything in the absolute value is inside my g parenthesis. Okay? Cool. Alright, let's go ahead and do one more. I know I packed 4 in here for you guys, but we're going to go ahead and trim it down just to 3 of them. We're definitely going to work on more of these Thursday, Friday, so don't worry, we will get to them. These are pretty hardy problems, and 3 of them, just like this, is substantial. Alright, so same deal. We're going to go ahead, first find that vertex. Your vertex orients you. It's like the center of your equation. It's the middle point of it, right? You find that, you find everything else around it. We are the equation whisperer, so we look at this and we can tell that it is going left 3. We look at this and it is going up 1. Okay, so our vertex is negative 3 and then up 1. We can go ahead and graph that, which would put it right about there. We can now also go ahead and start finding the sorry, lost for words, points around the vertex. So that would be a negative 4 and a negative 2. Okay, just picking some points around there. I go ahead and plug in those numbers. So I plug those in, and I'm going to see that, with a little bit of mental math, that negative 4 plugged into the function is going to give me a 3 over 4. Okay. If you're unsure of that, stop, work it out, do the fraction math, convince yourself it equals 3 over 4. Same deal with negative 2. Now, little pro tip. This is a parabola, so would you expect -2 to have the same output as -4, being that they're the same distance from the vertex, right? Would you expect a little bit of symmetry there? And the answer is absolutely. Now, can you still prove it? Of course. And if you want to convince yourself, and you need to convince yourself, go ahead and do the math for it. But it is also 3/4. Okay, so we get that. So we see our functions starting to come to life. We can plot those about there. We're having to estimate a little bit. Now we are on to bigger and better things. We are going to now find the x and y intercept. Okay, so I got the vertex. Let's go find the x and y intercept. The x-intercept, or, well, I guess let's start y-intercept. It's usually easier. We'll plug in a 0 for x. Remember, y-intercept, x equals 0. And so plugging in 0 to that function, we're going to see that we actually get out 0 plus 3 would be 3. 3 squared is 9. -9/4 plus 1 would become a -5/4. Okay, so our y-intercept is going to be -5/4. It'll be somewhere around there, which is good, right? Oh, I bet you guys are screaming Z-bucks. I totally just realized a doozy. I didn't place the vertex over far enough. That is my bad. I do not know how to count. Alright, cool. So I just magically learned how to count, and we are back on track and we're good to go. Now, something you may not realize, but very important to talk about, I was able to catch that mistake because of my graph, right? I kind of noticed that didn't look natural. It looked like this was a little bit too close to there, like it wasn't rounding out well. And so that told me to double check that and just to make sure it was correct. Little things like that, you're going to develop a skill for as you do more of these problems. All right, so we have our y-intercept. It's going to be 0, -5/4. Now let's go ahead and find our x-intercept. Remember, the dealio with the x-intercept is y is now equal to 0. So we have 0 equals -1/4 x plus 3 squared plus 1. Okay, we're going to do the algebra thing. We're going to subtract 1 from both sides. So we're going to have -1 equals -1/4 x plus 3 squared. So two things we're going to do here. First, we will divide both of them by a negative to get rid of those negatives. So we have 1/4 and 1 and x plus 3 squared. Now we have the fraction of 1/4 that's multiplying this. Well, how do we get rid of that? Well, a fraction is just division. So instead of dividing by 4, we're going to multiply by 4 to get rid of it. So we multiply by 4 on both sides. That would get rid of our fraction of 1/4. And then that would give us 4 equals x plus 3. Okay? Which is good, right? That's good. We're getting close to the answer. And we even see that when we get rid of that square by taking the square root, that is going to work out super nicely. Now, one small thing, notice what I just slipped in there, right? I wrote in a plus and a minus in front of my square root. That's something you have to write in front of every square root that you take. The reason for it is because a square could get rid of a positive and negative, so you don't know if you actually had your positive or negative there, so you have to account for both, kind of like an absolute value. If that confuses you, don't worry about it too much. Remember, you need to write that there, and we're going to have more conceptual talks around why that is. Okay? So now we go ahead and get here. So we have, this is going to become plus and minus and the square root of 4. Well, that's just 2 x plus 3. Okay, doing some more algebra, I'm going to subtract 3 from both sides. Now I have to remember, when I subtract 3 from both sides, not only do I subtract 3 from positive 2, but I also subtract it from negative 2. So that's going to give me two answers. Positive 2 minus 3 is negative 1, and negative 2 minus 3 is negative 5. Okay, just like that, those are our x-intercepts. We'll go ahead and write those in there. So negative 1, 0. negative 5 comma 0. And now on to the domain and range. Okay, so domain and range. And before I do that, notice, right, again, those estimates, right? If you take the time to plot a good graph, you're going to estimate a lot of this stuff. And if it's a multiple choice test, that can maybe even tell you what the correct answer is. So, anyways, so domain and range, right? Domain is how far left and right this can go. Range is how far up and down it can go. Well, I see this thing is spreading out pretty far, left and right. So I'm going to say the domain is infinite left and right, or negative infinity to positive infinity. And the range is going to go, right, how low can it go? Well, we see it dips down pretty far. So it's going to go down to infinity. And then how high up can it go? Well, it can go up to 1. And we're going to put a 1 parenthesis. Okay? That's the domain and range. Now for the transformation. Again, we're looking for the parent function. We want to know what is making this kind of U-like shape, or this parabolic shape. And if you know your quadratics, you know that's being caused by a x squared equation. So our parent function is just g of x equals x squared. That's a little bit cramped, my apologies. Okay, so g of x equals x squared. So notice, right, the x's are the same, so what is the square? The square is the g parenthesis. So we're going to go up here, we're going to replace the square with a g parenthesis. So we're going to write this as negative 1/4, because that would be in front of the square. G parentheses, because it's taking the place of that square. X plus 3 squared plus 1. Okay? And just like that, you wrote your general function form. And I want you to imagine this, right? Again, I know that part can feel redundant. It can feel stupid. It can just bring up all the worst parts of math for you. But think of it like this. If I got rid of everything else on this page and I gave you just this part down here, which I totally could do, you would be able to tell me this is being compressed by 1/4. This is being reflected vertically. This is being shifted left 3. And it's being shifted up 1. That's the whole idea of it. And we do see all those things in our equation. But this is a very general way of speaking of it. Okay. We're going to pause the video real quick. I need to get some water. My voice is kind of going. And then we will pick this back up. Okay. We are hydrated and back at it and ready to go. I just did that little dance thing that you guys do if you want to visualize that. It's pretty awkward. Okay, so I guess, yeah, let's go ahead and knock this ACT practice out real quick. Just a little bit of healthy practice for you. So, first off, right off the bat, what do you want to notice about this equation? It gives you a diagram, right? I mean, I look at this thing, I could tell you what the question is just by looking at the diagram, right? There's a variable, there's some angles. I need to find that missing variable. I need to find the missing angle. So you can read this to confirm that, and it says in the figure below, lines M and N are parallel, blah, blah, blah. Transversals R and S intersect, form the angle X. Two other angles are measured as marked. Again, all stuff that we saw in here, right? We could tell M and N are parallel. It's good to get confirmation. But all that other stuff, they're just restating what the diagram told you. That's why diagrams are beautiful, and you get everything you need from it. And look at that, what is the value of X, right? So we're going to go ahead and solve this. Now, before you solve this, two very important properties you need to know. Well, actually a couple, and that's why it's an ACT problem. First one, you are not crazy, right? If you look at this, and you see X there, and you see that angle, and you're like, but mister, what if? What if? That what if is completely right. These things are the same. That's a really cool thing about geometry, right? It's very visual, and if you draw things correctly and proportionately, you're going to see why it makes sense, right? We see how that looks like X. It looks just like X, right? It's about the same size. So that is X, right? Now, we are looking for this, and we can notice it's inside of a triangle. I have that angle, but I do not have that angle of a triangle. So here comes geometric property number 2. We can look at this whole thing, and realize, well, hey, that's a straight line, and it consists of 180 degrees, right? This whole thing's going to have to consist of 180 degrees. Oh, and it looks like I circled S. That's awkward. This whole thing has to consist of 180 degrees, which means that 100 would then need to be followed up by a 80 degrees in order for that to be true, right? Because that's the deal, is when a line intersects another line, those two parts right there, they have to add up to 180 because that constitutes a straight line. Okay, so those two things would have to add up to 180, so that's easy to tell that that one would be 80. And now at this point, the problem is very doable. If bells aren't going off in your head, they should be. You see a triangle, you should know the sum of all angles of a triangle is equal to 180. So triangle equals 180 degrees. That's when we can go ahead and make an algebraic statement of 65 plus 80 plus x would be equal to that. What is that? That is all the angles of my triangles. That's that one, and that one. Added together, they have to equal 180. Okay? You go ahead and you solve that, and you see that 180 minus 80 and then 65, well, that's going to turn out just to be 35. Okay? And so C is going to be your correct answer. And, yep. Okay, good little ACT practice problem. All right, let's go ahead and talk about inverses. So, you're smart. You know how to figure this out. I know you do, right? And I cleverly set this up just so you can look at this, pause the video. What's an inverse? How do you find it? What did I do to find it? And then what effect does it have on the graph? Okay, I'm assuming you unpaused it, or you just are a bad student and you didn't pause it to think about it. How do you find the inverse? You switched the red and you switched the blue, right? The x's became the y's. Sorry, x's became the y's. Y's became the x's. Notice, right? What did I switch here? I'm imagining a whole classroom full of kids saying I switched the x and y, right? That's all you do to find it. You just swap x and y. That's it. That's the inverse, right? Your input becomes your output becomes your input. You jumble it up, you switch them. Okay? You swap it, right? Notice, if it's a table, what do? You switch x and y. If it's an equation, what do? You switch x and y. If it's an inverse, what do? You switch x and y. Whenever you see the word inverse and it has to do with coordinate points, what should you do? Switch x and y. It does not matter what it is, you switch x and y. Cool. So now, what effect does this have on the graph? Well, it's kind of interesting because we have our y up here, we have our x down here, and when we switch them, it makes a diagonal reflection. Notice, we switch them, it makes a diagonal reflection. You see that dotted line. We switch them, it makes a diagonal reflection. So it's going to make a diagonal reflection whenever we do the inverse. And that's because we're switching that x and y value. Okay, so some things to look for. That's how we find it. Let's go ahead. We can do some of these problems to just make sure that we got it and we know it. All right. So the task at hand, graph the functions and its inverse. Make a table of values for each and state the intercepts. Okay, so quite a bit of things we got to do. Very healthy exercise for us. Let's go ahead and get going with it. First things first, I would just start by graphing your functions. Okay, so you see your function up here, 2x plus 1. Well, we'll plug in some points for there. Notice it's a linear equation, so I'm just going to plug in 0 to start with because it should yield a pretty normal number. So I plug in 0 and I get out a positive 1. So that can be my first coordinate point. Over 0, up 1. I can now start finding points around there to see what this line is going to look like. And I can plug in negative 1. And I'll see that that gives me out a negative 1. So right there. And I can plug in a positive 1 and get out 3. Okay, so I go over 1 and up 3, and it goes right there. So I have 3 dots. I can get an idea of what this looks like. Again, it's going to be a line. So we can imagine it looking just like that. Okay, now, right, you just learned what an inverse is. Go ahead and do it. So remember the inverse. And how do we write inverse? You write it like that. You put a little -1 in between the F and the parentheses. How do you do the inverse? You switch X and Y. Drill that in your head, right? Inverse, switch X and Y. Inverse, switch X and Y. Notice, did it make a difference for that one? Not at all. Inverse, you switch X and Y. Inverse, you switch X and Y. That is it, my friend. Okay, so we have those, and now it's just a matter of graphing our inverse. Right? It's not hard at this point. We're just going to go ahead and plot these other points from our inverse right here that we found. Remember, we switched the X and Y. And we're going to go ahead and plot these. So we have -1, -1. That one's already right there. That's nice. And we have over 1 up 0. That would be right there. We have over 3 up 1. That would be another one right there. And just like that, you can kind of start to see the line come into life. Right? And even if you notice, remember, right, what does the inverse do to the graph? What does it physically make the graph look like? It makes it look like a diagonal reflection, which is good. We can look at that and we see our diagonal reflection. Everything's making sense. This is good. Okay, so it says state the intercepts. We do want to go ahead and find the intercepts. So I have the x-intercepts, the x-intercepts right here. Or the, y-intercept right there. We want to find the x-intercept, and, you know, it can be pretty simple to calculate. You're going to see that -1/2 would be your x-intercept, which then means that 0 -1/2 would be your y-intercept on your inverse. And notice, right, that's good because it does approximate right about there on our equation. Okay, that model is lining up, everything's looking good. Now the very last part, right, so we did everything, and it's actually not that bad, right? That wasn't too bad. The very last part we gotta do is we have to find the inverse, meaning we have to write the equation form of it. Well, how do we do that? We are just going to do the same thing. You switch x and y. Remember, f of x represents y here, so we're gonna put a x right there and a y right there. So x equals 2y plus 1, just like that. And now you took the inverse, now you need to solve for y, so you can write it right there. So we're going to solve for y. This would be x minus 1 equals 2y. We subtracted 1 from both sides. We divide both sides by 2. Those would cancel, and we get x minus 1 divided by 2 equals y. Okay, that's our inverse equation. We'll go ahead and write it right here. And bada boom, bada bing, we're done. Okay, one small thing I want to point out. So an inverse equation is always going to give you back the same values that you plug in. So it's pretty easy to look at this and prove that these are inverses by doing a simple test. So what you can do is you can start by plugging in 0 for f of x. Okay, you pick a number, you plug it into your first function, and you see what it gives you out. And choose a number wisely so it makes your calculations easier. I chose 0, that's going to give out a 1. Okay, now to prove that it's an inverse, right, or give a good example of why it would be an inverse, we're now going to plug positive 1 into our inverse equation, right? And if this is a real inverse equation, it's going to spit back out 0. Right? Notice, it's going to undo that and bring us back to 0. So we're going to plug in 1 to this. We see 1 minus 1 is 0. 0 divided by 2 is indeed 0. And so these are inverses. Okay? Alright, let's go ahead and do another one. I know we got a couple on here. Let's at least just do 2 of them. And, well, I guess, yeah, we'll go ahead and do 3. What the heck, you can always skip it if you want. Yeah, let's go ahead and do 3. We'll talk about some other equations, and that will be a wrap. Okay, so same deal as before. Now, we're going to go ahead and find the vertex of this to help us get going. So our vertex is going to be 1, 3. We'll go over 1, up 3. We see our equation is going to be somewhere right there, kind of going upwards. And if you plug in your surrounding values, 0 and 2, around that vertex, you're going to see that you get out a positive 4 and a positive 4, which is good, right? That's what our equation looks like. Notice we found our y-intercept is going to be right there. Notice, are we going to have an x-intercept with this guy? Absolutely not, right? It does not go to the x value. It does not touch it, so no x-intercept. Now let's go ahead. Let's find our inverse values. So making our inverse table, remember, how do you find the inverse? You just switch x and y. So we are going to do 4, 0, 3, 1, and 4, 2, just switching those x and y values. Couldn't be easier, right? So we can now go ahead and start graphing this. So over 4, up 0, over 3, up 1, over 4, up 2, and you look at that, and it's coming to life, right? Right there, our other parabola, just like that. And we can even see that it is diagonally reflected. Okay, which is really good, right? Everything's making sense. That looks beautiful. There's some beautiful inverse functions. We're now going to go ahead and find the inverse of this with the equation. Okay? So remember, how do we find that? Well, we're going to switch x and y. So we're going to write x equals y minus 1 squared plus 3. Now, you may have already done stuff similar to this on Desmos. The only difference now is you're just solving for y. So you're going to subtract 3 on both sides. You get x minus 3 equals y minus 1 squared. Got to get rid of that square. How do we do that? Well, the opposite would be a square root. And we would get the square root of x minus 3 equals y minus 1. Now, one small thing, remember, you took the square root. There could have been a positive or a negative under there. So we're going to write plus or minus in front of that square root. Okay? Now, something big is happening here, though you may not realize it. Right? When we write that plus and minus, that technically means there's two equations going on there. There's the positive one and the negative one. And so, using some different colors, we could actually take a closer look at this and see the positive one, right here, would be this arc right there. It would be the upper branch. And then we would see that the lower arc, right, we'll use blue for that one, for the negative, that lower arc would be right here. So notice, the inverse of this is made of two equations, right? Why is that? It's because of the way our square root function works, and it's because of us needing a positive and a negative when we take the square root of something, right? So for everyone who noticed how a square root is kind of like half a parabola, you're completely right. It is half a parabola. It's half of the inverse of a parabola. Okay, so we'll go ahead and finish off this problem. We will then write plus or minus the square root of x minus 3 plus 1 equals y. That is our inverse equation. We'll go ahead and write it down. And I should actually be saying inverse equations because there's a couple there, right? There's the positive and the negative version of it. But those two things together make up our inverse equation. Okay? And you can even, just to kind of drive home, right, the two branches of those positive and negative versions, you can look at this and you can see those versions kind of manifested and reflected over here. You see that green line, right? That corresponds to the green branch. And you see the dark blue branch, right? It corresponds right there. Okay? And so they relate to each other. It's just that the first one could be expressed with only one function. The second one needed two functions because there could have been a plus or a minus. let's go ahead and do one more. These are definitely not too bad. Same deal as before. We're going to graph this. How can we graph it? We're going to find the vertex. So we're going to put -3, -2 is our vertex. Up, not up. We're going to go right there. Okay? And so that gives us a starting point. We can now start to plug in points around there to get an idea of what this looks like. So I'm going to plug in -4. Notice when I plug in -4 to this, oh no, I'm taking the square root of a negative number. So there's no solution to that. Now I'm going to plug in -2. That would give me square root of 1 minus 2, which would be a -1. So back 2 and down 1, just right there. Notice I'll start connecting these, and it's going to look something kind of like this. Okay? What is the y-intercept of it? We'll go ahead, we'll plug in 0. That would be, and notice we can't simplify this, it would be just square root of 3 minus 2. Okay, and that's going to be somewhere actually right below here. Square root of 3 is less than 2. So square root of 3 minus 2 would be something less than 0. Alright, now let's go ahead. So same deal as before, we're going to go ahead and find our inverse coordinates, writing our inverse like that. And we are now going to, remember, just take the inverse and just swap your x and y values. So we're going to go ahead and swap them. We're going to get out square root of 3 minus 2 and 0. Swap them, 1, -2, swap them, -2, -3, swap them, no solution, -4, and there's no solution for that, right? It does not work. Okay, we can start graphing these. We're going to go down 3 over 2. We're going to go down 2, back 1. And we're also going to have a point right about there that's going to cross. Just like that. Okay. I just realized one point that I didn't find on here is my x-intercept. So we do want to calculate that really quick. So we'll do the work for that up here. 0 equals the square root of x plus 3 minus 2. Well, that would be 2 equals the square root of x plus 3, which would then equal 4 equals x plus 3. Notice I took the square of both sides. I squared both sides. And then that's going to go to x equals 1. Okay, so we plug in 0 for y, and we get out x equals 1. So there's our coordinate right there, and then there's the inverse of it right there. Sorry, it's getting a little messy right there. But so again, you can see our equations, and if you draw your dotted line diagonally very carefully, you can even notice, right? You still see that perfect reflection, which is very good. We're now going to go ahead and find the equation of it. And remember, we're just going to swap the x and y. We have the square root of y plus 3 minus 2 right there. And now we need to solve for y. So doing a little bit of algebra, we are going to get this. We're now going to square both sides. And you notice, right, that parabola just perfectly pops up. You know, it just kind of comes into being. It comes into existence just when we need it. And we're going to go ahead and subtract 3 from our final part. And we get x minus 2 squared minus 3, which equals y. Just like that. That is our beautiful inverse equation. Let's go ahead and write it right there. Nothing feels better than putting the final part in an answer. Minus 3. And just like that. Regular equation and the inverse. Along with all its intercepts, both of them graphed, and it is beautiful. Okay, let's go on. We will skip this one, save it for later. Now, so just some basic questions. So those tests we did before, we're going to do them again. So are these two functions inverses? Well, absolutely, right? Now, you can tell that by looking at them, but here's how you prove them, right? You're going to pick a number. You're going to take g of something. You're going to pick a number to plug in there. What am I going to choose? I'm going to choose 2 because I see 2 would work out nicely there. So I plug in 2. That's going to give me 2 divided by 2, which goes to 1. Now remember the inverse, I should be able to give an inverse that same coordinate point, and it should spit out the original coordinate point. So I'm going to go to f of x, plug in 1, 2 times 1 is indeed 2. It looks like these are inverses. Okay, that works, that is excellent. Now another thing you can do, and this is one other thing, is you can actually plug one function into another. And this is going to trip you guys out. Just look at that, right? We just took one function and we plugged it in. If you thought it was crazy enough, we just stuck a function in a function, right? So now we have 2x, because that got plugged in, that was our f of x, divided by 2. Okay? Now, why do that? What's the point of it? Well, you're going to see, right? And this is a more general way of testing to see if it always works. Right? You plug that in there. You're going to look at that and you're going to say, well, what can I do with that? Well, I can cross out my 2's. And that's going to give me just x. Which is good because the definition is if your inverse function, if your function undoes your inverse function and gives you out just x, they are inverses. Okay, well, I'll say that again. If this undoes this, or if this completely counteracts it, you're going to get out just an x, right? This one got undone by this one, or this one got undone by this one, whichever way you want to think of it. And they gave you out just the original x value that you plugged in. Hence, you plugged in an x, you got out that same x. It did it, and then it undid it. That's the whole idea with it. So these are also inverse. Okay. All right, same deal with this one. We can go ahead, we can pick a point to plug in and just see if that works nice and easily. I'm going to use a little bit of foresight. What number am I going to plug into there? Well, I see if I plugged in a 3 there, negative 2 times 3 would be negative 6. Negative 6 and negative 4 is negative 10. That's going to give me an even number to divide by. So I'm going to plug in a positive 3. Like I said, right, that positive 3 would create a negative 10 on top. Negative 10 divided by 5 would be a negative 2. Okay? Now we come over to our other function. We're going to write f of negative 2. And we're going to plug it in. So I plug in negative 2. And now this one doesn't work out as clean. That should immediately tell you something's not working nice here. Right? You get negative 10 plus 4 times negative 2 over 5. And that's going to equal negative 18 over 5. Was that the number that we started with? Heck no. Absolutely not. Right? These are not inverses. That does not work out. So these are not inverses. Okay, you could go ahead and prove it the way we did before, like right here, by plugging a function into a function. So g of f of n, which would be equal to, and you just do your negative 2, you plug in everything up there, so it would be a negative 10 plus 4n divided by 5 minus 4 divided by 5. Okay, and you should be able, and then notice that looks more complicated. It's a little bit more difficult to compute, but as you start to calculate it, you're going to see that, you know, it gives you another answer that you can't really do much with. It's going to give you 20 minus 8n divided by 25 minus 4 over 5. And you know, you're not crazy, you look at that, there's not really any way that's going to work out. These are not inverses. Okay, and the main idea there was that, right, when you had your function and you plugged it in, if these were truly inverses, they would have gotten rid of each other and given you back the n, right? But they're not. The same way that you plugged in a number, it gave you -2, you plugged in your -2, and it did not give you your original number. They don't map onto each other. They're not inverses. They don't go back and forth indefinitely. Okay? Alright, so are the two inverses? We're going to go ahead. We will run a test with a number. What's an easy number to plug into here? Well, let's pick 3. Right? 3 minus 3 would be 0. That's going to zero everything out. That makes it very nice for us. So we're going to pick h of 3, which goes into 3 minus 3. And I'm showing the work here. I know a little bit different, but you know, sometimes it's good to show your work, especially if you're struggling to get your computations correctly. And that would be 0, okay? So h of 3 brings us to 0. We're now going to go to f of x and plug in 0. Okay, plugging in 0 for that. We're going to see, right, that would make 2, 0 to the third, plus 3, which then just equals 3, aka the number we got out. So these are inverses. Alright? Now one small caveat, just because this works with a single point does not ultimately prove that they are inverses. And that's why we do have our variable test to see if these will work even when we use variables. But the odds of it working for a random point that you choose and not being inverses is very slim. So that's why this test is almost always going to be accurate. But we'll go ahead, we'll do it the authentic way. We'll plug in f of x to h of x. Remember, just putting that function where we see the x. So it's going to be 2x cubed plus 3, got plugged in up there, minus 3 divided by 2. And we start to calculate. Now notice things are going to happen very nicely here. And when they are perfect inverses, you see things just kind of start to melt away. Right? We take away the parentheses, and you immediately notice those 3's, right? What are they doing to each other? They cancel out. So you get the cube root of 2x divided by 2. Well, again, right? Look at that. What's happening? Those 2's divide out. Oh, my apologies. Forgot to write the cube on there. Those 2's will divide out, and that's going to equal the cube root of x cubed. And again, right, they perfectly cancel, giving you that x, which means they are inverses. Okay? Let's go ahead. One last question, then we will cut the video. So, a function has a domain and range of these two things. All right, so that is our domain, that is our range. What is the domain and range of the inverse? So remember, now, just pause and think about that for a second, because honestly, you might be able to find it out on your own. If a function has this domain and range, what's the domain and range of the inverse? Okay, pause it, think about it. I'll tell you how to do this. So remember, if you remember one thing, this is very easy, and it's a very easy conceptual question. So domain, right? It correlates to a variable. What variable does it correlate to? It correlates to x. R, it correlates to a variable. What variable does it correlate to? It correlates to y. Range correlates to y. So inverse, what are you doing with those x's and y's? Right? You're switching them. So you're going to switch your x and your y, which also means you're switching your what? Your domain and your range. So the inverse just gets the domain and range swap. Just like the x and y, just like a domain and range associate to x and y, you're going to switch them. So now this becomes your range, this becomes your domain for your inverse. Right? And that's it. So your range, and we'll go ahead and write this correctly, the domain would be infinity, bracket 5, and then parenthesis, oh, I'm sorry, wrote that wrong, bracket -2, comma infinity, parenthesis. How did I do that? I just looked up here, and swap them around because it is the inverse.